In this video, I want to do a couple different examples of a test hypothesis using the rejection region method, just to get you comfortable with the technique and hopefully to show you that it's not overly challenging. That you're gonna. I had a conversation with you guys in confidence intervals, and I said my goal was for you to walk out of the lecture thinking, I can do this. This isn't too terrible. Well, I guess that'd be my same goal here. And so the two examples, the first one, according to the National Funeral Directors Association, the nation's 22,000 funeral homes collected an average of $7,180 per full service funeral in 2014. So we took a random sample of 36, kind of an important number we'll get to in a second, and they reported revenue data for the current year. Among other measures, each reported its average fee for a full service funeral. So this number here, the 7,180, that's being given as a population mean for 2014. And we're talking about the current year. We've sampled 36 and it's reporting its average fee. That'd be an X bar. Conduct a test of hypothesis to determine if the average fee collected in the current year is less than the average collected in 2014. So we need to come up with a null and an alternative hypothesis. We want to see if the average in the current year, that's going to be a mu, we're going to look at it through the eyes of X bar, but we need to see if that mean is less than what it was in 2014, which was $7,180. That's what we're trying to show. That's what we work with as the alternative hypothesis. And then we just dump in there an equal sign for the null hypothesis. There are three pieces that you have to figure out when you're identifying the test hypothesis. The first step is to formulate or identify the test. You have to identify the parameter, and we can see that that's an average, mu. The specific value you're interested in, 7,180, that's pretty obvious. And then a direction, and we're looking less than. That's it. You got to go through the story, and you got to come up with a parameter, a direction, and a number. And that direction that you're trying to show is the alternative. We're going to begin by assuming the null hypothesis is true. And so we put an equal sign there. There are three options for this alternative. There's a less than, a greater than, and a not equal to. You got to figure out which one is appropriate for the words of your prompt, for what you're trying to show in the current example. And then that goes in the alternative. Equal sign will always show up in the null hypothesis. Now, when I go to the computer, and I'm going to show you the output of the computer in just a second, but when I go to the computer, it's going to ask for this piece here. It's going to ask me to specify, usually it does it by a variable of interest. What's the variable? Because you're going to go and I actually selected a menu that said something like test a hypothesis for a single population mean. And I think, well, in another video, I'll show you how to generate the printouts, but mu for the average for, and I would choose the revenue. That would be the variable I use in this case. The average revenue, it asks me the hypothesized value, the 7,180, and then it says, what do you want to test? Which direction? It assumes the null hypothesis is equal, but it says, do you want to do a less than, or greater than, or not equal to? And the software that I use, that we use, actually gives us a choice, and we have to select it. All three are listed there. You just pick the one you want. And so the next step is to calculate a test statistic, and this is where we need that printout, and you can see I've generated it here. Now, the printout, the data that was collected, the data in this particular problem, this comes from the textbook that we're using, the data was given in thousands of dollars. So if a funeral cost $7,000, it would just list it as 7. If a funeral cost $7,500, it was listed as 7.5. So I had to represent the 7,180 the way the data was represented, so I did it that way. So what you see here is the null and the alternative, and a lot of times I'll have students ask, why do I need to know it? It shows up on the printout. Well, the reason it shows up on the printout is because I asked for it. I put in the 7.18, I put in the less than sign, and I chose the one sample test for a population mean. You can see here's the variable that I selected. This is the test statistic. Now, interestingly, in the software we're using, we don't get large sample tests. It never gives us a large sample test. But one thing we learned is that T distributions look like Z distributions as you get larger sample sizes, so it doesn't really matter. So we're going to use this same menu for both large and small samples. Now, why am I saying it's a large sample? because my sample size is 36. For means, a large sample is 30 or more, a small sample is less than 30. For proportions, it's something different. And we looked at it when we talked about confidence intervals, and we'll look at it again when I do test hypothesis for proportion in a coming video. But n is equal to 36. This is a large sample. That's why you're going to see me write this test statistic. And even though it shows up on the printout as a t, you're going to see me write it as a z is equal to negative 1.71. That's what our data suggests. Now, let me kind of review an idea with you. If the null hypothesis is true, we would expect our test statistic to come from a z distribution. We collected our sample, we did our math, and when I say we, the computer did the math, and we got a negative 1.71. The question I have for you, does that look like it comes from a z distribution? Is that expected or is that unexpected? And the reason I'm asking the questions and phrasing it this way is because that's what the rejection region asks us to do. We got to figure out whether our test statistic, whether that negative 1.71 is expected or unexpected. And when I ask you that, does it come from a z distribution? A lot of you guys are probably going back to the earlier in the semester and you're saying, well, we expect most things to fall within 3 standard deviations of the mean. So we expect our z-scores to be between plus and minus 3. And that one easily is between plus and minus 3. And that would be a very Chebyshev approach. And some of you are saying, well, Chebyshev doesn't work. We're dealing with a normal curve. We should use the empirical rule. It should be plus or minus 2. And I'm going to say, okay, that's an empirical rule approach, but you can do better now. You guys should know a lot about the normal distribution. And I'm using the normal distribution because I have a large sample. So I'm going to use a z distribution. We know the value is 0. And again, you're going to hear me say this a lot, but I am drawing with a mouse, so grace and mercy. And so we want to figure out cutoff points. And those cutoff points depend on 3 things. The first one is the z, which I've already drawn here, the large sample. The second is our choice of alpha. And in this particular problem, we want to be 95% confident. The way we typically say it in a test hypothesis setting is we say alpha is equal to 0.05. So you need to know the curve, whether it's a t or a z, because as we've seen with small samples, we'll talk about t distributions. We need to know what our alpha is. And now there's a third piece. There's a direction. We have a less than. What we're used to doing in confidence intervals is taking that alpha and splitting it and putting it in both sides. And that's appropriate if we're doing confidence intervals or not equal to tests, where you're interested, is it bigger than or less than $7,180? But that's not what we're asked here. We're asked, is it less than? And so we're going to take that entire alpha and we're going to put it in the less than side of the curve. So we're going to put 0.05 in the lower tail, the less than tail. If it's a greater than test, we're going to flip it around and we're going to put it in the upper tail. If it's a not equal to, we're going to split it and put it in both tails. So you got to consider the size, the sample size, that gets you the t or the z. You have to consider what your alpha is, and you have to consider the direction of the test. But once you have all those things considered, now you should be able to go to your table and find what this cutoff or what this critical value is. And actually, for a lot of values of alpha, there's a couple different ways you can do it. There's the z distribution technique, where we look up, the table that I tend to use is the inside probability. So we look up this 0.4500 and find that it falls somewhere between 1.64 and 1.65, and we typically use the number 1.645, and this would be a negative 1.645 because we're below the mean. Or you could go to the t distribution that has 0.05 in the tail and go all the way down to the bottom of that table, because those bottom numbers you see in those columns are z values, and you'll see the number 1.645. You'll have to add the negative sign because we're on the left, but that's what gives us this rejection region. At alpha equal 0.05, we reject if z is less than negative 1.645. And I'm going to change my ink color now. So if our test statistic is further out there in the tail, now notice if I change the alpha, that's going to change this number, right? If I change the direction, that's going to change this number. It's going to change where I'm at on the curve. If I change the sample size, I may have a small sample problem, that's going to change this z distribution. So there's lots of pieces that can move here, but the process of coming up with a rejection region is extremely consistent. All right, so the rejection region says here's when we can reject. The conclusion says, well, what are you going to do in this case? Our test statistic is negative 1.71. Where is that? Well, That falls further out here, right? Negative 1.71. If I plotted it in this picture, it'd be in the rejection region. So we have a situation where the test statistic is in the rejection region. We can reject H naught. There is sufficient evidence to indicate that the average fee collected in the current year is less than, now where did this stuff come from? There's sufficient evidence to indicate that the alternative is true. When we reject, there is sufficient evidence to indicate that the alternative is true. We can say, and now we're just going to put the alternative into words, there's evidence to indicate the average fee collected in the current year is less than $7,180. Fees have gone down. That doesn't happen very often. That's the conclusion we make. Now, before I leave this idea, okay, we have the 4 steps, the test statistic, the rejection region, the conclusion. What do you think would happen if I change this number to 0.025? Well, here's what wouldn't happen. The null and the alternative wouldn't change. The test statistic wouldn't change, right? They would stay the same. But that would change, right? If I change that 0.05 to 0.025, if I put smaller probability out here in the tail, this number would move that way. It would move further out in the tail. In fact, I'll give you the number. It becomes a negative 1.96. Now, the reason I'm bringing this up, if we used a 0.025, and this was a negative 1.96, what would happen to your conclusion? Is a negative 1.71 further out than this number? It wouldn't be, right? 1.71 falls between those two numbers. It is further out than the 1.645, but it's not further out than the 1.96. And so at a 0.025, that's a 2.5, if you can believe that, we would, I'm going to add 2 letters here, we're going to fail to reject. There is, what would we say in that case? Insufficient evidence to indicate that the average fee collected in the current year is less than $7,180. So what I want to point out is we can make either decision. Obviously, you want to make the correct one, but most of the wording doesn't change. If you reject, there's sufficient evidence. If you fail to reject, there's insufficient evidence, and everything else stays the same. Those are the 4 pieces of the test hypothesis. Test statistic, rejection region, conclusion. There is another technique. This is the rejection region technique. There's another technique called the p-value, and if we look on this printout right here, there's a p-value right there. Now, it's going to be a preferred method. I'm going to say I prefer the p-value method because some of the work gets transferred from me to the software. And I'll bring this up. I'll raise this conversation with you when we have our p-value discussion in a later lecture. But just know that it's going to get even easier. Okay, this piece here, the rejection region, finding that cutoff point, that's on you. That's your responsibility. Comparing the test statistics to the rejection region is usually pretty straightforward, but you are responsible for that guy. As I change my alpha, as we saw, the rejection region changes. Sometimes our conclusion changes. If I made alpha 0.10, well, if I made the alpha bigger than this 1.645 numbers moving this way, we're still going to reject it alpha equal 0.10 because a negative 1.71 is going to be still bigger. Maybe it moves over here somewhere. So that's how the test hypothesis works. Let's take a look at another example, and I'll wrap up this video. So in this one, what happens to student exercise when they learn in an online environment? I wonder why I might be thinking about online. That question was investigated in a recent study. 210 students were randomly sampled and asked how many hours they exercise per week. It is believed that traditional live face-to-face learning students, I couldn't think of any more ways of saying that, so I put them all in the one place. It's believed that when we have a traditional, hey, we meet in class and do the typical thing, they average 7.5 hours per week. Is there sufficient evidence to indicate that online students exercise more than 7.5 hours? Why would I think this? Well, you might have more time now. You're not having to run to and from campus. You might be bored. Who knows? I'm asking, is the population mean now bigger than 7.5? So your job is to come up with the null and the alternative. What are we trying to say? Well, we're trying to say the mean exceeds 7.5. That's all we need to come up with the null and the alternative. The alternative is greater than, the null is equal to. The test statistic, well, I got to go and get my sample. Went to the computer. My average in my sample was 8.1333 hours. My test statistic is 1.32. There you go. Again, notice there's a p-value out here. We'll get to that in, again, another video, but it's right there on the printout. That makes this third step easier. If you're using the p-value approach, what I'm going to tell you to do is just state the p-value, 0.0950. Now, again, I'm going to have more conversations with you. I'm going to explain it. There are a couple little hiccups or challenges with the p-value that we'll talk about, but by and large, I think it's an easier process, and we'll get there. Today, in this video, let me go back to the red. I like red. In color, here we go. Oops. What's our rejection region look like in this one? Well, 210 students. It's really tempting to say, is that a large sample? Well, it's bigger than 30, but is that the appropriate criteria? Yeah, I'm working with averages. It's greater than 30. That's what I'm supposed to look at. That tells me to work with the z-distribution. It's always centered at 0. I have an alpha of 0.10. Where do you put the alpha in this case? Well, again, we have three choices. Sometimes, like in the last example, it always goes in the left-hand tail. Sometimes it goes in the right-hand tail. Sometimes we split it and put half alpha in both tails. How do we know? We look at the direction in the alternative. It says put it in the upper tail. Put it in the greater than tail. So put 0.10 up here. There's your alpha. And find this cutoff point. This is not a cutoff point we've seen before, I don't think. You can find it from the t-table. You could go down the 0.10 column in the t-table all the way down to the bottom. I know I'm talking large samples and using t-tables, but a lot of us know it's an easy way to get some t-value or some z-values. It's simple. You'll see the number 1.282. If you look up 0.40, that's a 0.4000. If you look up that number in a z-table, you don't see it. It's in between 1.28 and 1.29. It's closer to the 1.28. I'm going to use the 1.282 number I get from the t-table. If you prefer to use a z-table and make that 1.28, that's fine. That'll work too. And our test statistic in this case, again, I'm going to change in color again. Our test statistic is, wow, just barely, right? 1.32. 1.32, just barely bigger than the 1.282. But big enough. It's further out in the tail. It's in the rejection region. So our conclusion is to reject H0. And this is wrong. It shouldn't say 0.1. It should say what? 0.10, right? Somebody didn't copy and paste well enough. That should say 0.10. Sorry about that. So in your notes, make that a 0.10, not a 0.05. Oops. That's a second typo I've caught now. At 0.10, we reject H0. There's sufficient evidence to indicate that, and I'm going to say this in the words of the problem. Online students exercise, on average, more than 7.5 hours per week. Mu is greater than 75, or 7.5, excuse me, 75 hours per week. Wow. That'd be crazy. At alpha equal 0.10, we reject H0. There's sufficient evidence to indicate that online students exercise, on average, more than 7.5. Now, in the last problem, we used the 0.05, and I didn't catch that when I copied and pasted some stuff over. If I use a 0.05 in this case, this number would be 1.645, and the 1.32 wouldn't be further out. So at 0.05, we'd fail to reject. There'd be insufficient evidence at 0.05. That's the test hypothesis. It's the same 4 steps. It's a 4-step dance. Identify the test, get the test statistic from a printout. Sometimes you have to create the printouts. Most of the time, I'll generate them for you. On your projects, you'll be generating. On exams, I'll be generating them. State the rejection region, or stay tuned and learn more about a p-value, and then make your conclusion. So get to work. Take a look at some examples, some homework problems. Do some work. Make sure it looks good to you. Ask questions. Get online and ask the questions when you have them. Don't let this stuff pile up. Final exam's weighted heavy. You need to get this stuff. The sooner you get the test hypothesis material down, the easier the final exam is. So get to work, and if you have questions, you know how to contact me. So long.